So this is NCCER Instrumentation 4, Module 2, Proving, Commissioning, and Troubleshooting a Loop. So, page 1, you're going to have, like it says, Proving, Commissioning, and Troubleshooting. Like they have Proving and Commissioning are both trade terms. Everybody usually knows what troubleshooting means, but you need to know the difference between all of them. So knowing commissioning and proving in those trade terms is going to be good to know. Continuity tester, just know that continuity is checking what? Just to make sure there's a connection. Continuity just means there's a connection, usually in resistance or something like that. Ground loops. Anybody remember what would cause a ground loop? Ground loops are the, It's the, you remember with, you guys might not know, but with instrumentation cable, what's important about the shield and the drain wire? Remember that?
You take it off, but it can't be touched.
It's only connected on one end. So it drops the electromagnetic interference off. You guys will get that in the lower level instrumentation stuff. But if you hook it up on both ends, you can make a ground loop where you're sending current through the ground, and that's bad because your grounds are connected everywhere, and trying to narrow down what's putting current into their ground is you have to go unwire everything. So ground loops are the toughest to troubleshoot. Loop checking, proving, selling. You should know what selling is a step in the process. You should know what that is. My first highlight is the paragraph in the top right, the sentence that has proving, and the two sentences after are highlighted. The second step is proving. This task involves simulated testing and calibration of the various components in the chain. A live process is not used at this stage. So the things you want to key in on is simulated testing, no live process. That's in the proving stage. The immediate next two sentences are a separate highlight. The next step is called commissioning. This incremental step involves extensive documentation and using live processes to continue the testing. So when you think of commissioning, think of extensive documentation and using live processes. For our purposes, they're talking about, this is kind of talking about like the factories where I've worked, where we buy a piece of equipment or something that's going to like make something or something like that. They send their technician out to install everything, and they have to go through the steps of like loop checking, proving, commissioning, selling. Like I've always been maintenance at a facility, so like usually the companies will go through and do all of that, and then they call it like a turnkey operation, and then they turn it over to the maintenance staff. So they have to have like the documentation saying that we checked this wire and this wire, and we checked like they have to make sure that they check everything before they turn it over to the maintenance staff. Mechanical inspection, or this is in 110 loop inspection going on to 111 mechanical inspection. I got the second and third sentence highlighted, which is the last two sentences. The materials and components installed may also have been damaged during installation, or they may have arrived from the supplier in an inoperable or damaged condition. For these reasons, among others, it is necessary to verify the mechanical installation of all instrumentation loops before assuming they are ready for calibration or normal operations. Take a look at stuff like when you guys go through the lower level instrumentation books, they talk like it might even been in one and you already had it, but we talk about like accepting materials from shippers and stuff like that. Like, don't accept everything off of a truck and assume that it's good. My younger brother and best friend, well, brother changed jobs, but they both work for the trucking company XPO. Probably seen like just says XPO on the side of the trucks. They used to be called Conway. Conway was a big trucking company. They told me about where they have what's called the Conway crunch. And that's where you turn a forklift backward, like if the door's not closing at the back of the truck, turn the forklift backwards and ram it into there, close the door, and it's the next person's problem. They've both told me they've been getting better about that, but people do that. People will break something and wrap it up, send it on, not my problem anymore. So make sure, like this crap's expensive, so make sure that you're checking stuff, and you never ever want to take possession of something and be like, oh, that was broke. Like, you signed the paper, so wasn't broke technically. So
Yeah,
just
you went over that.
okay. So that was in one. So just making sure that like a visual inspection takes 30 seconds, and you can check even like we talked about, like the sight glasses on the front of a pressure gauge and stuff like that. Even if that breaks, like you guys just went through and saw the inside of or showed you a picture of the inside of the pressure gauge and saw the little bitty gears and stuff like that, little shards of glass can get in there, mess stuff up. Just all it's saying is make sure you're doing a visual inspection of the mechanical installation. Next paragraph, all the way in the bottom right, first sentence. The first stage of verifying mechanical installation is a visual inspection of the loop, starting with the primary element and ending with the final element, which is usually a control valve. The PowerPoint up here, like having a PNID is especially useful for checking a loop. Remember, a PNID is just going to show you the interconnections between stuff. It is not the physical layout. So whenever you're doing a visual inspection, it might be good to have, I get you a big drawing like this, and have a red pen or a highlighter and say like, all right, that's that valve, or this is that accumulator, like this looks good, this looks good. Like somebody could like the methanol plant that's in the back, like that was bought as a skid. Like you can buy like stuff like that as a whole. People come and test it out and stuff like that, and then I think that's actually the PNID for back there. Like, whereas like the little loops that you're doing out here, like yeah, you have the little control valve and the pressure transducer and stuff like that. That's easy. But whenever you have to walk around and it's a big facility and stuff like that, it's nice to have something to kind of reference. Flipping over to page 2, last paragraph before 112, first sentence is highlighted. In addition to checking for damage and improper installation, the mechanical check also includes confirming that components are of the correct size and rating. Hopefully stuff that's bought is rated correctly and stuff like that, but yeah, just checking the correct rating. Remember I don't have anything in primary element or the field transmitter, but remember like the primary element is the first component that comes in contact with the process. So like the trainer out there that's right outside the door, like taking level of that tank, you got that pressure transducer. That pressure transducer is your primary element, and then like you guys will eventually do that, and then your final control element would be the control valve that you're sending a signal to put air into. So just knowing what the primary element is. Nothing in field transmitter. 114 field wiring, conduit, and tubing. I've got in the top right of the page, top right of page 3, first full sentence up there is highlighted. Slightly damaged signal wiring or broken conduit can cause intermittent problems in the control system. A lot of the wiring and stuff like that is not stranded wire. So moving it around, like it's the little bitty solid core wire and stuff like that, and the more you move it and bend it and stuff like that, the more brittle it gets, or the more like everybody's taking a piece of wire, bending it back and forth till it snaps or something like that. Just be aware of that. Like it's very easy to have intermittent problems, especially if you see like a lot of times with conduit, it's somebody that didn't put the conduit nipple on tight, or the little O-ring on the inside of the box gets loose as over time, and then that'll come out, and then people will step on it, and then those wires are sitting on the inside of that knockout hole. cutting into the sides of the wires. So you can have intermittent problems with that. Control loop components, 115, nothing in that. But do note, I know for a lot of control rooms, especially if you're working nights as a maintenance person down here, air conditioning is super important. Like if you get, I know when I was at the steel mill and stuff like that, we would have air conditioner units that went out in like our big MCCs and PLC rooms. PLCs have a sensor on them. If they get above a certain temperature, they're going to shut off. So that's like usually those control rooms and stuff have a placard, or at least ours did, had a placard that said if we had a contract with the HVAC company, if something happened, if they're on call 24/7, those guys were always pissed off when we called them. But I don't know how to work on HVAC stuff or industrial equipment and stuff like that. But even if you walk in somewhere and notice that it's hot, PLCs do not like hot environments. So that's just something to check. Moving on to 116 on page 4. Tag numbers and loop sheets. I probably tag numbered y'all to death between the first 3 levels of instrumentation. The first sentence is an online test question for tag numbers. Tag numbers are unique numbers assigned to each component of the loop, all sharing the common loop number as part of their tag number. I'm not going to talk about that at all because I feel like you guys have gotten that enough to this point. Section 120. Checking loop continuity. First sentence. I guess it's the first paragraph is highlighted in 120. Loop continuity tests involve applying a signal generated by test equipment to the wiring or tubing of the loop to determine if the signal passes through the complete loop without leakage or excessive resistance. So, like I've done that in the back with a couple of classes where we go out there and they have like pressure transmitters. Something like this is back there that's getting I'm wrong. On control valves and stuff that are back there, control valves are getting like a 4 to 20 milliamp signal from your PLC that's set from your HMI. And like back there, you can change the control valves from 0% to 100% open or closed. And I usually have somebody out in the on the machine itself, and they'd use little alligator clips, and they clip to the 2 wires going out there, and they can see whenever I set it at 25%, if it's at 8 milliamps, and 50% is 12, 75, 16 milliamps, 100%. 20 milliamps, and that's saying that whatever I'm putting in on this side of the wire is coming out on this side of the wire, and that's called loop checking. Electrical continuity test 121. Second paragraph, last sentence. You'll have a couple questions come out of that. Ideally, you should select a device that can energize a loop using its own power supply. I keyed in on that. Using its own power supply, allowing the loop's normal supply to be locked out during testing. So that's where you can have a process meter that can actually put out a signal. Is that the leadership books? Yeah, they came in today.
Yeah.
I'll give them to them on Monday.
Monday?
Yeah, because this isn't them.
I'll take mine.
This is my night class.
Yeah, I'll take mine too.
Yeah, you can give those 3 there.
I'm about to say, wait a minute. I'm recognizing
We taking night classes too.
Come on.
We like your so much to stay. How you doing?
Smart people.
Sorry.
The smart folks.
I'll get the other people. They won't be in tomorrow, but I'll get it to them on
I'll
Monday.
hold it. It'll be in my office.
Okay.
Thanks.
So you can come and get them anytime.
Yes, sir.
You said you keyed in on what one?
Key in on,
Using its own
they
power?
use it, yeah, using its own power supply. So the process meter can actually output 4 to 20, they can output like a 1 to 5 volt signal or 4 to 20 milliamp. And that way you can have everything shut off and then just input this with something with its own power supply. Same section, last paragraph on the right hand side, right before 122, first sentence is highlighted. With the newer smart instruments that now make up many of the loops controlled by PLCs and distributed control systems, it is necessary to connect a precision resistor, so plus or minus 1% of a resistor of 250 ohms into the circuitry in order to simulate the load or the loop load. So it's always good, like once you get in the instrumentation world, I think last week, I can't remember if I showed you all, but like the little stinger stuff to plug into a pressure transducer, like you want to have one of those, and then also like a 250 ohm resistor. Like that's just something you kind of keep in your bag. Have one of those. Yep. In the simplified methods, so this is with using just a digital multimeter. So you can go out there, and that's where I was talking about. That's what I've done out there is look for like a 4 to 20 milliamp signal. So you can see in that picture, like they're just testing to see. That still looks like a process meter. This is still a fancier meter than just a regular digital multimeter. But you can check with just a regular digital multimeter rather than having a process meter. Flipping over to page 6, that first full paragraph, first sentence is highlighted. A tone tester pair is an excellent way of confirming basic continuity that requires just one person. So looking down there at the bottom, have you guys seen these? Have I shown y'all this? That stuff, this equipment? Give me 2 seconds. So this is called, the technical name is a toner, but at least at the steel mill I worked at, a lot of them called it a Fox and the Hound, which is a name brand. It's like saying Kleenex for a tissue or something like that, or whatever. But you can check in continuity and stuff like that. I don't necessarily use it for continuity. I use these for finding wires that I don't know where they go. So I can turn this on tone, turn this on where it's on, and then you have, like, you would connect this to like 2 of your wires, like one to ground, one to whatever wire you're searching for. And then like this thing can check through walls and stuff, or like getting close to ceilings and stuff. I just push my button, and whenever I get close, you can find which wire you're talking about. So if you're ever going in behind somebody trying to find out what they did or where a wire's going or something like that, this one's a little fancy because it's Fluke and I didn't have to pay for it. But you can get like personally, I have a Greenlee one that works as good or even a little bit better than this. I think I paid $75 for it. Definitely a useful tool for like tracking stuff down. They're saying use it for continuity. I'd rather use a regular meter for continuity than that. But if I was checking just for continuity for one wire going out there, I'd probably unwire it, twist the 2 sides together, and then use my digital multimeter on the other side and check for resistance and make sure I had low resistance through the entire wire. Pneumatic testing 1, 2, 3. So did I show you all this little hand pump last time?
Yeah.
Yeah, so this like $1,000, and then you have the pressure. You had, like, I had the crystal gauge on the other side. I don't have the meter for this, but I do. Like this is the one with the pump, but I do have a crystal gauge. It's not exactly like this, but it's a high dollar gauge that's super accurate, up to 1,000 psi or something like that. But it's just pumping up one side and then making sure that you're seeing that pressure on the other side. My highlight for 1, 2, 3 is in the top right of page 6. I guess it's the second paragraph up there. The one that starts with Fluke. I've got the first 2 sentences of that highlighted. Fluke, GE Druck, Weka, and Crystal Engineering all make suitable units. Some calibrators require specific pressure modules to be added to the basic unit. That's where it's just saying, like sometimes you have to have a pressure unit that goes along with the crystal unit, This one has both in the same one. This one has a pump and the sensor in the same one. I don't have one of these because they're, I guess just because I didn't order them. They're expensive though. That's all I've got for that section. So I'm just going to keep going. So for homework and stuff, you'll do the section reviews, but I'm just going to keep going for the sake of the video and stuff like that. But you'll just have everything to do for homework before class on Tuesday, then we'll take the test. Section 2, proving and calibrating a loop. Current loop trim is going to be important. I think we talked about that in the last chapter, but it's just adjustments that are made during the third stage. So that's a good one to know. Management system, sensor trim, zero and span calibration we talked about, that being the most basic calibration standard, but it's the most basic, but I use that one the most. In my experience, I've used it. Zero and span way more than I use like a 3 or 5 point calibration. My first highlight is first paragraph, last sentence. Proving begins with the process of checking actual loop functionality by operating it under controlled conditions. What did I want y'all to remember about proving?
It's simulated.
Simulated process, and what else? Simulated testing.
It's not live.
Not live. They're not using live process. Simulated testing using something that's not live testing. Proving a loop 210, second paragraph, last 2 sentences are highlighted. Last 3 sentences are highlighted. However, proving does not involve live or wet process. Instead, it substitutes simulated process. This is done for both convenience and safety, since a loop may still harbor hidden problems at this stage. It's also done because if you're installing something like a big system or something like that, you can say like, this part of the system is good without turning on everything. Like we had, like in the steel mill, we had what was called a degasser project, where they actually took like the molten metal and put it in a big pot, and then put a vacuum on it, and then put different types of chemicals in it under vacuum and stuff, and like big process. It took a year to build, and this, that, and the other. But I actually went over there and like, we need you to check this part and make sure this is good, so that way they can say, okay, this is good, let's keep working on this. But because I couldn't turn anything on because the project wasn't done. So proving would just be like you're doing incrementally sections saying this should be good whenever you turn it on, is essentially what you're doing. That's where I've seen proving. Whereas like if somebody was installing one piece of equipment, that would just be part of the process. 212 at the bottom of the page. Required test equipment. I've got starting from there all the way, that whole first paragraph is highlighted. Proving a loop requires test equipment that can supply the loop's power or energy, whether it's air or electrical. The device must also be able to read the output signals of each of the instruments in the loop, regardless of their signal forms. Volts, milliamps, PSI, etc. If the loop includes signal conditioners or transducers, it may be necessary to have more than one piece of test equipment on hand in order to read the various intermittent signal forms. However, test and calibration equipment that provides all of these functions in one unit is available. Out to the side of that, I wrote multifunction calibrator. That is a multifunction calibrator that can do all that stuff in one unit. You'll need to know that for the question that's. We'll actually have a couple of questions come out of that, but.
I assume those are expensive too.
Huh?
I assume those are expensive.
Yeah. Like I'd have to look at. I have one in the closet in there. I'll have to look. I can look back at. See how much I spent on that. But you can see that multifunction process calibrator. But then you also have the pressure. The pressure modules that go along with that. Look down there. Like, I mean, anything that's got the name Fluke on it's going to cost 25% more than a lot of the stuff. Fluke and Crystal are both high dollar stuff. But Fluke is also usually the best. Like, it's definitely not cheap equipment and whatnot. Testing the programming, page 11. First paragraph, last sentence is an online test question. But if a PLC or programmable controller is involved, the software component must also be tested as part of the proving step. If you've ever messed around in a PLC and stuff like that, I know at least the Allen Bradley and GE versions of PLCs have a test function in them, to where you can go into that and make sure the code that you wrote is good and stuff like that. And you can kind of simulate the process inside the code without downloading it to the system. So you can essentially check all your code before downloading it into the PLC. Online test question.
What was that again?
213 first paragraph, last sentence. But if a PLC.
Okay.
Calibrating loop 220. Weird how they. Calibrating a loop. I've got the second sentence to the end of the paragraph highlighted. I have a couple questions coming out of those sentences. Calibration should not be confused with loop tuning. They are completely separate stages. The loop cannot be tuned until it has been calibrated. Tuning is covered in a separate module of this curriculum. So calibration is one thing. Calibration is making sure that, remember, calibration for that system is saying if I have a 4 to 20 milliamp span or range, then my 3 to 15, they're proportional all the way. That's calibration. Loop tuning is saying, I want this tank to fill up faster than it is, so I'm going to change the gain on my control. Y'all might remember changing the gain so that the valve opened up even faster and stuff like that. That's tuning. That's not changing the calibration at all. That's changing how the whole system works. Does that make sense?
Mainly for a speed thing?
Yeah, it's saying I open up this control valve faster. If you're turning the gain up, you're saying send a higher signal even faster to this. But anybody remember why that can be dangerous? Not dangerous, but unwanted. Some people might say, well, you just open up the valve all the way as fast as you can, right? But if I've got my graph, say I have a 100-gallon tank, and I want to say this tank, my set point is 50 gallons, and I'm starting at 0, and say I turn my gain up super high, right? The disadvantage of that is, well, say my gain is where I'm supposed to be. Ideally, you should be going to this and then slowly making it to your set point, right? But if you're saying turn my, I want this to get there faster, what it's going to do, you're going to miss it.
Right.
And then you'll be like, oh, crap, I went too high, so it's going to, the gain can work the opposite way and shut that valve all the way. And then it's going to go, and then you can actually get to where you'll never, these can actually get bigger and bigger and bigger because you'll never make it to your set point. So it's important to tune, tuning a loop is not just making it do it the fastest. With all instrumentation and loop checking and tuning, you want smoothness. Smoothness is way more preferential than quickness in this. The slower you can make things work, the smoother stuff's going to be.
Right.
Loop cannot be tuned until it's calibrated. Calibrating analog instrument loops. 221 on page 12. I've got the second sentence highlighted. I guess second and third sentence. The normal calibration adjustment involves only setting the 0 value and the span value because they're is effectively only one adjustable operation between the input and output. This procedure is often referred to as a zero and span calibration. I feel like we've talked about that enough. 222 calibrating heart instrument loops. The last paragraph on the page that starts on page 12, and then the beginning of that all the way through where you see sensor trim on page 13 is an online test question. So in the first instrument stage, the microprocessor converts the digital count to an internal representation of the sensor units, so temperature, flow, pressure, etc., by using an equation or lookup table. The manufacturer creates this table or equation during production. However, it is possible to tweak this stage in the field. Doing so is referred to as adjusting the sensor trim. Adjusting the sensor trim, like that's what you want to key in on. That is an online test question. Connecting the heart communicator, 223. The whole second paragraph is highlighted going into the next page. And you're going to have a couple questions come out of this one paragraph. If the smart transmitter is used in a digital-only instrument loop with a PLC or DCS, for example, only the first instrument stage requires calibration. If the transmitter must provide a conventional analog 4 to 20 milliamp output signal, both the first and third stages must be calibrated. Note, the third stage calibration is independent of the first stage and has nothing to do with the zero and span settings. The second stage does not require calibration. So that's what you never, the second stage is the factory lookup tables and the characterization. That's what we talked about last class, or the class before last lecture, last chapter, where you never ever change the factory characterization. That's in the second stage. 224, asset management system. This is something I feel like I might have talked about in Instrumentation 3. I've never been in a place that has had stuff like this. It would be awesome to have. Essentially what it is just a system that you have every component in the plant, and when it was installed, when it was calibrated, when it needs to be calibrated, when it might be due for service. Like there's plants out there that have all of this information for you, and anytime you go calibrate stuff, you go update the documentation. Anytime you have to change out a part, you go say, I put this part in there. Like that stuff would be great. I've never had that anywhere I worked. And honestly, I think for somewhere that's already built, I think to me it's too daunting of a task to try to do that. But if you were building a new plant or something like the Venture Global plant, like massive plant. But if you could get somebody whose job was they know what all they're putting in, they're buying all of it right now. Like if you could get somebody to have this management system, like that's going to help maintenance immensely. Like during.
We have that in our plans.
Do you really?
Like every single component, we have a serial number, we have everything about it. So like whenever we just go look at the map, it says this component,
That
we
must
ordered
be,
the XX.
must be nice.
Yeah.
Because like I've changed out components that don't have a word or a number on them at all.
Motors, anything, electrical
like-
or instrumentation wise, like
Yeah.
plastic, everything.
Nice.
Yeah, which is nice. Yeah.
Just know you're a little spoiled.
Yeah.
I'm just saying, it is not like that everywhere.
Yeah.
My highlight for this, I highlighted just the blue instrument asset management system, and then drew a line and pointed to the first two sentences of the second paragraph. Where control systems are concerned, asset management goes beyond simple inventory management. Instruments and other control components require maintenance and regular calibration. This sentence that starts in the bottom left through the end of the paragraph is also highlighted. They can report their settings, calibration status, maintenance history, and current operational performance. As the device starts to wear out, their performance values change, which can be an early warning sign that maintenance or replacement is needed. You have stuff that'll tell you what
Every single one of our machines, everything that we build, like my department, every single thing that we build is intertwined like that. So like we know before it fails, and if we know why it failed.
I don't know why, but that annoys me because I haven't had that like.
Well, like the guy who designs most of the stuff, like the ones we keep talking about with Marty's name is Robert. He's a crackhead. Like he designs, builds everything by himself, and
He's got you on video saying Robert's
yeah, it's okay. He'll appreciate it. We actually have a trophy. There's like a little crackhead trophy. He's got it multiple times because of that. But yeah, no, he's
Yeah, that is
yeah
immensely beneficial.
So like each component he puts, and when he builds a machine, like a screw has a part number that attaches to either a Mech Masters or a Ranger number, and you can just literally order that screw, and that's for a screw. And he goes, huh? Interlocks. Yeah. So anything that comes out of Meg, that's like that. Which is insane.
That's awesome.
Yeah.
Next paragraph, first.
Dude, it's insane. Like,
First 3 sentences of that next paragraph are highlighted. Instrument asset management systems are software packages that run on a network computer or server. They communicate with smart instruments and keep detailed records automatically using rules established by plant personnel. They can schedule calibrations, alert technicians of impending failures, and help keep track of everything without the need to do so on paper.
yeah, he built everything too, like the software side of it. It doesn't look fancy, but it tells you the machine number because each machine number he numbered. So it's like, yeah, like,
Where is that?
I don't know, like MS7.
That's the, right after the last highlight at the top of the page.
Okay.
It's the first 3 sentences, so instrument through the word paper.
Gotcha.
Probably, I don't know, 7 or 8 lines.
Got it.
So you'll have the section 2 review, moving on to the section 3. I'm not doing the best with keeping up with the PowerPoints, but that's all right. Commissioning a loop, talking about, you might have heard of somebody saying stroking a valve. I know I had somebody from Instrumentation 3 ask me like what that meant. That just means moving a valve from all the way closed to all the way open, and making sure there's no like, sounds like a fake word, but it's called stiction. Like valves, like the stem of a valve can actually like get stuck along the way and stuff like that. I'm sure that'll pop up at some point. I think that's the word. But just making sure that a valve operates smoothly from 0% all the way to 100%, whether it's opening or closing. That's called stroking a valve. First paragraph, last 2 sentences are highlighted. Of course, the system will not be accepted without tangible and well-documented proof that everything works as specified. Warranties hinge upon good documentation as well, so this step requires as much paperwork as it does process and testing. So what do I want you to think of when you think of commissioning a loop? Extensive documentation. Commissioning takes extensive documentation.
Where was that at again?
My last highlight was on page 16, first paragraph, last 2 sentences. Starts with, of course, right through the end of the paragraph. Gathering the documentation. They're talking about all the drawings and stuff like that. The first bullet point I've got highlighted as an online test question. Piping and instrumentation diagram, P&ID. The P&ID shows the method of control. Key in on method of control for a given process along with the approximate device location and tag numbers. I wouldn't say that. I guess a P&ID might give an approximate location, but just know like it just shows the interconnections, not necessarily exactly how stuff is laid out. Still going on in the bullet points on the right hand side, I've got the hardware installation detail drawings, the whole bullet point highlighted. These drawings show the actual mounting, orientation, and connection of each instrument and control device. They can be helpful when troubleshooting instruments that require special installation procedures. The next bullet point, first sentence is one highlight, loop diagrams. These are the most referenced drawings during proving, commissioning, and troubleshooting procedures. The next sentence is a separate highlight. They show the connection details of the control system and the components arranged in a loop. So you can actually see that up on the board. So it has like the field process area, the panel junctions, and then the control room. So you can see how loops are made. So I've got a power supply right here. So the output goes to terminal 2 in the panel, and output negative goes to 11. So then you can see the actual loops that are going out from 10 and 9 going to, looks like a pressure transducer, or it is pressure transducer, that measures 60 to 200 inches of water, right? And then you've also got signals going in here, like the signals coming from the panel junction terminal block 4 are controlling that air operated valve down here. But that's a loop diagram. The next bullet point, the whole thing is highlighted. Instrument index. This lists the instrument tag numbers for all instruments or control system components, including the associated drawing numbers, materials, specification sheets, and other related information for each component. A lot of highlights on these 2 pages. The commissioning process, 320. First 2 sentences of 320 are highlighted. Many of the steps carried out in commissioning are similar to those carried out in loop checking and proving. However, in commissioning, these steps are more formal and thoroughly documented. You get questions on documentation, more than likely it's referring to the commissioning step. Page 17. On that started paragraph that started on page 16, about right in the middle, I've got 3 questions that come from these 2 sentences. Tests are typically done in stages where the loop is first operated in manual mode, and then increasing degrees of automation are added. At the end of the process, tests are done with the loop in its normal operating configuration. Out to the side of that second sentence, I wrote automatic mode. So at the end of that process, you put it in automatic mode to make sure it works. Good? They have the steps for a typical procedure. I've got step 3 highlighted. Verify that instruments have been calibrated. This is normally done by the instrument manufacturer, but may be required as part of the proving procedure. You can read through the rest of those steps, but I don't have anything else highlighted through step 9 or through the end of that section. So you'll have section 3 review, and then finally we've got troubleshooting, which in my opinion, like that's what I'm teaching y'all how to be maintenance people. I'm not necessarily, I mean, sometime in your career you might get to a point where you're hired on by a company. Like if you don't mind traveling and stuff like that, you can make a lot of money going and installing specific pieces of equipment in different factories and stuff like that. But usually you're like a 1-person crew going in and installing everything. But they make pretty good money, have per diem and stuff like that. But it's just a lifestyle that's different. Like it's hard to have family and stuff like that. But if that's you, like that's something you can make a lot of money. Usually later on. Usually after you get like 5 years experience and people know that you can work by yourself and stuff like that. You can get jobs like that where you're going through this whole process on your own, and then at the end, like giving it to the plant. For our purposes, I'm talking to y'all as you are or will be maintenance people. Troubleshooting a loop. You have what's called cavitation. Cavitation is bad. If you've ever the trainer that's right outside the door here, if enough water has evaporated out of that tank and you fill up the tank on top, that motor will start sucking air, and that's called cavitation. Very, very bad for motors. You don't want motors to do that. Oscillating process, this is what it's talking about for oscillating process. So you don't want something to do that. That would be an oscillating process. Fundamentals of troubleshooting a loop. I don't have them highlighted, but those 5 steps, like identifying the problem, identifying components, understanding the loop, troubleshooting the loop, repairing or replacing instruments in the loop. whenever I was working in maintenance, what's step one? I'm getting ahead of myself, but what would be step one of being a maintenance person? If somebody had a problem?
Ask them what happened.
Talk to your operator. Talk to your operator, because you're not gonna, I mean, Brandon, you might be a little bit different if you get into maintenance because you've worked at Domino for so long. You know how stuff works. I was hired on as an electrician at the steel mill, and I didn't know how stuff worked. So I would go and say, like, what's this doing and what's it supposed to be doing? Because I can understand how stuff works if I know what it's supposed to be doing, and then I can find out like what's going wrong and stuff like that. But for most of the processes and stuff like that, I didn't know what it was supposed to be doing. Talking to having good operators is key. Like a lot of times, if I'd have an operator that had been there for like 20 years, I'd usually get there and be like, "It's a solenoid that." Like good operators are key. And then you can have operators that don't have a clue, but they usually know how the equipment works, and you can decipher what's going on with that. Talk to your operator first. Identifying the problem. 411, the first two sentences are highlighted. Troubleshooting a loop starts with identifying the problem in the loop. A problem recognized by an obvious system or through the operator's observation over a period of time. As the technician is responsible for troubleshooting, you must listen carefully to the operator's complaint. Sometimes operators do complain about little stuff that either can't be fixed in the moment. Like it's usually something like, dude, I'm gonna have to fix that whenever we shut down. Like I'm not gonna be able to go in there and tweak. Like you're gonna have to deal with this crap for, like sometimes there's operators that are like, this is annoying. Like, sorry, like you're gonna have to deal with it till we have to shut down the whole process and stuff like that. But obviously you don't want that attitude, like going and talking to somebody. Listen to their complaint, and then see what you can do or find if there's a remedy. Be like, let me know if y'all shut down today so I could go take care of that in 10 minutes, but I have to be locked out. But y'all are still able to run now. Does that make sense? They go through like actual questions that you can ask and stuff like that. I don't have any of that highlighted, but going on to page 20. 410, 411. First paragraph, first two sentences on page 20 are highlighted. Another troubleshooting tool is the documentation history or maintenance record of the loop. All facilities keep maintenance records that list problems and remedies of previous faults with the loop, if any have occurred. Do y'all know if y'all keep maintenance records and stuff like that? That was couldn't put a price tag on. We had it was just called a log book. So whatever you worked on that night, it had a drop down of equipment. You go pick and specify the equipment, and you say what the problem was, and then you put what the remedy is. And you could search that database, and whenever a new technician or somebody else, like I was looking at stuff from people that were gone for 5 years where they had fixed something, and I go in and like, that's so much easier, like at least getting a clue of what to do rather than going in there blind. Like if you work somewhere that doesn't have logbooks, get them to buy a system that will do logbooks. It's a very simple program that is invaluable. Second paragraph, first sentence is highlighted. Reoccurring problems in the same loop may indicate underlying cause that has not been located or resolved correctly. If something has the same problem over and over and over again, whatever you're doing is it's a band-aid. It's not fixing it. You're just getting it to the next shift or something like that. So it might be to where like if you're inexperienced or something like that, like you go to a more experienced person or a supervisor and be like, hey, this is doing this, and I've been doing this, and it's been temporary, but I don't know. Like we need to go further dive into this and see what the actual problem is. Nothing highlighted in 412, identifying loop components. 413. Understanding the loop. First two sentences are highlighted. It's about half the paragraph. If you do not know how the loop works, It is impossible to troubleshoot it. This does not mean that you must learn how to operate every loop in the process that you were called upon to troubleshoot, but it does mean that you should have a high level of confidence in your ability to understand what the loop is supposed to do as part of the process. And that's why you talk to your operators. And that's why you guys get into maintenance and stuff like that. You get on, I worked on swing shifts where I worked 4 days on days, 4 days off, 4 days on nights. Nights was like, we had skeleton crew running and stuff like that, and usually you're walking past the maintenance office and the guys are kicked back, feet are on the desk, passed out, something like that. That's something that you can do, or you could be a little proactive. I would go hang out in we call them pulpits, but there's operator stations and stuff like that, and just kind of shoot the shit with, like, get to know your operators and stuff like that, to where like we got raises and stuff based on, like, they would send out the maintenance supervisor would send out surveys to operators, and our raises were based on how much people liked us and stuff like that. Sort of. But it's so much easier to work on stuff whenever you know the person and can talk to them and stuff like that, and go hang out with them. And like, operators would let me do, like, run stuff for a little while. I'd get to know how stuff worked, rather than just sitting in the office on my phone or something like that. Like, yeah, that's easy and stuff like that, but that's not the way to, like, you can get so much more out of just going and talking to
Yeah, I
somebody.
walk around a lot.
Just go talk to somebody for an hour. Like, makes their day easier, makes your job easier and stuff like that, especially in the beginning of this stuff. Or learning, especially if you're new in the plant and stuff like that. Last sentence in that same paragraph is highlighted. You should also be prepared to question operators and other technicians or supervisors, as well as observe the process. I feel like that's kind of the same thing within setting. Nothing else. I've got nothing else highlighted on 20 and 21. Going into, like, 414 is troubleshooting the loop. First paragraph on page 22. I've got third sentence highlighted. In testing the loop, you could begin at the power supply and verify that you have 24 volts DC. Whenever you're like, there are a lot of different methods of troubleshooting, but I will say this, like, if you have a loop, start at one end or the other. Don't start at the middle and try to guess your way through what's going on. And usually always starting at the beginning and making sure stuff has power, that was usually 60% of the problem. Like, something happened where a breaker was tripped, a fuse was popped, something's going on, or somebody crushed something at the other end of the line. Like, start at one end or the other. I've worked with a lot of maintenance people that'll just, like, go ask them what's wrong, or be super impersonal. Like, we had in our office, we could log into PLC screens on the other side of the plant, and people would try to talk to an operator on the phone and just get into the PLC and see what's going on. Like, go look at what's going on. Like, it might not be obvious to an operator what's going on, but you might look at something and be like, just doing a mechanical inspection or visual inspection, be like, that's not, like, somebody busted the conduit off the side of that, and the control wiring is busted off, something like that. Go to where the problem is, and start at one end or the other, like the power supply, or all the way at the other end. They go through, like, the steps on like page 23 was saying, like, it has a specific problem, and then it goes through the steps on how to fix it. I would recommend, like, this is good stuff to read. I don't have highlights on page 23, but it's good to have an idea of what you're going to ask. Especially, like, whenever I was a brand new technician and stuff like that, I was super nervous, and my confidence level was super low. And I didn't know how to, like, I also, before becoming a teacher and stuff like that, I didn't talk a lot to people and didn't have good, like, personal skills and stuff like that. So having an idea of, like, what you're going to ask and how to talk to people, like, it's good to have.
I feel like that's what we're doing now. You know, like,
Kinda, yeah. Like, you're getting introduced to a lot of new people and stuff like that. But it's just better when you have an idea of what to do. And even, like, I had the advantage of, like, we had shift partners, and you usually had, it was like unofficially official. Like, we had a shift lead, but it was just whatever electrician had been there longer. kind of, we had a couple electricians that had been there for a long time that sucked, but,
That's what they're trying to implement right now, that we're going, it's gonna last them.
having shift partners,
Yeah,
I think it's a good thing,
like,
because you can
I'm supposed to
learn.
run a line, or at least 2 lines, and if I run into a problem that I don't already know about, I can call for one other guy, you know? Instead of asking for anybody.
But it'd be like I'm saying, like, say they put either one of y'all with Nick.
Yeah,
Like, you can learn so much from him, because he's been there for 3 or 4 years.
yeah,
Like, that's kind of how they did it where I worked. Like, having somebody that had been there that knows a lot, and you can sit there and pick their brain and stuff like that, and even, and another thing with that, like, build your confidence with this stuff up, because I know there were some times whenever I was an intern at Goodyear, or not at Goodyear, at the steel plant, and like we had 4 people and they're troubleshooting one thing, and in my mind I was like, maybe like I can't remember exactly what I thought of the solution, and
yeah,
I didn't say a word,
right.
and 4 hours later they figured it out. And I
Well,
was like-
I mean, the guys are
Should've
kind of
said
hard-headed, like, this could be the problem. They'll hear me say it, but then
You'll
until they
always
find out that that's the problem, they're like, oh,
Well, that's a personal thing. Like, that's not necessarily like a thing that everybody's gonna be like that. Like, you always have to have an open mind. Like, when you guys get 10 years down the road in maintenance and stuff like that, just remember that. Remember that, like the new guy could have an idea and stuff like that, and maybe 80% of the time, like, it's nothing, but 20% of the time, like, hey, he's gonna save us a couple hours on this. Something like that. Just try to be a little bit confident, like, hey, and say it as a question. Don't say it as like, it's this.
Right.
Like, say it like, hey, why would it not be this? And they can either explain why it's not, or they can be like, I don't know. Like, and then like go try something like that. Like, it's all like, it sounds weird, but it's all like kind of how you talk to people.
exactly.
This is still in the troubleshooting techniques and stuff like that. On page 24, the last sentence before 415 is highlighted. Start wherever your instinct tells you to start, but always be systematic and logical. I say start at the beginning or the end of the loop, because that's what's logical to me, is start at the beginning, check your power supply stuff, and then work your way down. Is how I work. Like, sometimes people might know, other times you might be like, oh, I've seen this before, and go check something right in the middle, and that's what it is. But once you've been a maintenance person for a while, you'll kind of get the instincts and stuff of what's going on with certain pieces of equipment. You kind of, we had equipment that we named, what did they call it? Like we made the big steel coils, and we had what's called a coil wrapper that would actually wrap like it would run through the eye of the coil, and it would wrap plastic, and I think it was called Lucy. They called it Lucy the bitch, because like the thing would mess up all the time, and it was an old piece of equipment. But you almost kind of get like a feeling of that, my dad worked in the same place, and he was like, he had a love-hate relationship with that thing, because he was a mechanic and go work on it. Like, he knew everything about it, but it was still a piece of shit. 420 troubleshooting and oscillating process. So that would be that. Something that's not finding its set point. The first 2 sentences of 420 are highlighted. A very common problem in some control systems is an oscillating process. This is a process that continues to react to a disturbance rather than returning to stability after a reasonable period of time. Good. Nothing in 421 or 422. I'm going to read through those on your own. 423, identifying possible causes of the problem. The paragraph that's after the bullet points. First 2 sentences, you're going to have a couple questions that come out of that first 2 sentences of that paragraph in the bottom left of 25. Controller operation is the easiest and most likely initial check to make. A controller can often be ruled out as a cause of the problem simply by shifting it into manual and observing the controller and its process response. Sometimes, like I know not all of you have worked on it, but that be like the trainer that you're working on, like like you were changing the output today in manual mode, right?
Right.
Sometimes, and you were doing that to, like in the very beginning, like to see if you could match whatever that valve that was halfway on, if you could match how much water that was putting out for how much water you were putting in. Sometimes in order, like I've put a controller in manual mode, and I've been the kind of the sensing thing and see. Once I get to a set point, I can get it close and then pop it into automatic mode, and then it will take it from there. It's usually taking it from like all the way at 0 to whatever the set point is the hard part of a controller. But if you can manually get it there, then pop it in automatic mode, it'll usually take off. But getting it to that point, like something's wrong with the loop tuning, like the gain set too high or something like that. But if you just need to run, put that joker in manual mode and get it there yourself, then pop it in automatic mode. That doesn't work every time, but it's worked for me in the past. Checking instruments in the field, 424. I've got all of step 1 highlighted. Visually check the output gauge on the transmitter. If the gauge is oscillating, it indicates that the transmitter output is oscillating. Oscillation in the transmitter output could be due to a problem in the transmitter, the valve, or the process. Step 2 is also part of that highlight on page 26. Check the instrument's air supply gauge to the transmitter. If the transmitter is receiving a pulsating supply, it could cause the oscillation of the transmitter output. Alright, that's actually all of my highlights for this chapter. Let me stop this